Hello folks, just a quick help with a review for the exam. Pretty much most of the definition you should be able to look up in your notes and straightforward. So I'm going to skip this page and focus on the skill-based part of the test for your handwritten part. So once again, I will provide you with most of the equation and Planck constant, and you know what, I'm just going to be nice on the speed of light too on your handwritten part of the exam. So with that, you only are asked to know how to use them. So let's figure out this question. I'm trying to find the wavelength of a light, and I'm given unit of joules, which is energy. So I'm given energy, but I'm trying to find wavelength, which is lambda. And as we can see, we don't have lambda and E in any of the equations. So that means it's the two-step problem. So first, you only can do things based on what you're given, which is energy. So we're going to use one of the energy equation to solve for something that's not available. Well, with the energy equation, we already know E. We know H. So the only thing left is nu, which is frequency, or that curve V. So let's do that. So E equal H nu. Let's go. We know E is 9.8 times 10 to the negative 19. For now, I'm just going to ignore the unit. Equal H, which is 6.626 times 10 to the negative 34. Ignore the unit times nu. So to get nu by itself, since this is a multiplication problem on the right, I divide the number in front of it by itself. And I'll get rid of it. But whatever you do on one side, you do to the other side, because that's what the word equal represent in this case, or the symbol equal, I shouldn't say the word. So with that, when I punch it out on my calculator, let me go 9.8 double E negative 19 divided by 6.626 double E negative 34. I get nu equal 1.479. Let's just make it 1.48 times 10 to the 15. Okay, so now that I know that, I can erase all this stuff and I continue with that same logic. I know V. I'm looking for wavelength again. What is the only equation that has V in wavelength? It is speed of light equal lambda times nu. Now let's plug it in. C we know always, because it's a constant in the universe. So plug that in. Equal wavelength we don't know, times nu, which we know now because we had the foresight to at least trying to find out something instead of giving up on the previous equation. So now I'm trying to find lambda, and I want it by itself, so I want to get rid of what's next to it. And since it's multiplication, we do the opposite, which is division again. And what you do on one side, you do on the other side. So wavelength is simply 3.0 times 10 to the 8 divided by 1.48 times 10 to the 15. And if you were asked for a unit, the unit for wavelength should be something in a meter. Just to review again, nanometer equal 1 times 10 to the negative 9, because nano means a billion of. And then if you see frequency like megahertz, mega means million, which is 1 times 10 to the 6. And hertz is 1 over second. Nanometer, because this meter is still meter. So with that, let's look at the question here. What is the frequency? So we're looking for nu. With a wavelength, well, the only equation that has both of those is the speed of light equation right up here. So with that, pretty straightforward. C equal lambda nu. Let's plug it in. C is always 3.0 times 10 to the 8 equal to wavelength, which is 3.2 nanometer. We just say nanometer, which is times 10 to the negative 9. I'm just going to ignore the unit for now. Okay. And then frequency is what we have left. So to get rid of the wavelength that is being multiplied by the frequency. Since I'm trying to find frequency right here, I just have to divide the number in front of it by itself. And what do I do on one side? I do on the other side. Punch it out and you get your frequency, which is going to be 1/2, which represent hertz. Okay, fill in the following chart. Energy level 1 has only S because there's only 1. S can only hold 2, so 1 times 2 is 2. Energy level 2 has S and P because 2 can have 2 subshell. S has 1 orbital, P has 3, making 4. 4 times 2 is 8. Level 3 has 3, S, P, and D. S is 1, P is 3, D is 5, making a total of 9. 9 times 2 is 18. Level 4 has S, P, D, and F. Once again, continue the logic. F is 7, D is 5, so 12. P is 3, so 15, plus 1 more is 16. 16 times 2 is 32. What does S look like? S is a sphere, it's a ball. P is the figure 8, or known as the infinity symbol. Remember, it can go in the 3 dimension, X, Y, and Z. So Z, imagine if it's inside out. Commonly, it has a nickname, dumbbell, like the weight that people use to work out their arms in the old days. So P is also known as a dumbbell. Okay, D is clover leaf shape. So if you see 4 lobe, it is a D. No matter how you rotate it, in the left to right diagonal, right to left diagonal, in and out diagonal, and out and in diagonal, it is still the same shape. Label the wavelength. Okay, the amplitude is from the middle of the wave up to a peak or a trough. So the amplitude is the height of the wave. The wavelength is the distance between a peak to a peak or a trough to the trough. It should be the same thing. Technically, you can also label it from one location to the exact same location on the wave. So as this is going down, this is also going down. Therefore, all of those are the same thing, wavelength. Crest is obviously the tip, and the trough is the bottom, like a trough for animal to eat. What is the frequency above? So, pretend this thing is, say, 10 seconds. 0 to 10. Your frequency is the number of wave divided by time. So let's count. 1 up and 1 down. That's 1 wave. 2 wave. 3 wave. 4 wave. 5, 6, 7, 8, 9, 10. 10 and a half. So this has a frequency of just a little bit over 1. If I were doing it out on a calculator, this has a frequency of about 1.05. Or if I just use my common sense and move the decimal over by 1, since you're dividing by 10. Wave per second. So this is 0 second and this is 10 second. Okay, whichever radiation has the longest wavelength, the longer your wavelength, the lower your frequency is. So let's use your common sense. Higher frequency, high energy. So we know gamma is going to be the highest frequency. So this is going to be frequency down here, since the number seems to be increasing. And radio wave is pretty safe around us, lower energy. Therefore, the lowest frequency is over here, since 10 to the 4 is a lot smaller than 10 to the 22nd. So we know the bottom line is frequency. The top line, therefore, has to be the opposite, which is wavelength. Because the lower your frequency, the bigger your wavelength is. So radio wave has the longest wavelength. The answer is radio. Which type of radiation has a frequency of 10 to the 6? We go to 10 to the 6 over here. And we see it is AM or FM or radio overall. But in this case, it's mostly AM. What is the relationship between wavelength and frequency? The higher the frequency, the shorter the wavelength. And the lower the frequency, the longer the wavelength. So they're inverse relationship. Which type of radiation has the longest and shortest frequency? I would say the highest and lowest frequency to be exact. But the highest frequency is gamma. Sorry. I misread that. My fault. Which one has the longest wavelength? as radio again, because radio has the longest wavelength over here of 10 to the 4th. Gamma has 10 to the negative 14, so it's shorter. And which one has the shortest frequency? The shortest frequency is, guess what? Also radio, because longest wavelength equals shortest frequency. So either way, it's radio. Write the configuration for the following element: copper and silicon. We did this in class many times, but 1s2, 2s2, 2p6. I'm doing this from my head. I don't have a periodic table, so I apologize. 3s2, 3p6, 4s2, 3d9. But whenever we end with a d9, we change that to a 10. And take 1 from the s, because you don't get free electron found anywhere. So it becomes 4s1, 3d10. Silicon, okay, let me see. My brain is a little slow right now. Let me see what's the atomic number for silicon as I'm typing it on my computer is 14. So let's go 1s2, 2s2, 2p6. That makes a total of 10. So we end up with 3s2, and that's 12. We finish off with 3p2. Adding up all the superscript, we should end up with the atomic number for silicon. Continue, same thing. You can do that. Let's try to see. Let me look up periodic table. And with that, okay. So write the noble gas configuration for the following: nobelium. Let me see my periodic table that I just Google. Nobelium is number 102. Okay, so I go down to 102. And we write the shorthand way. So nobelium is in the 5F, which is in the 7 row. Since 102 is in the 7 row, so we go up 1 over. And the last noble gas in the previous row is radon. We do a bracket over it. And then we just count the row that nobelium on, which is row 7. So we start out with row 7, 7. And S matches the row because it starts at 1, you know, for row 1, 2 for row 2. So on row 7 is 7s2. After 7s2, we have that big jump. So we know we're going to go to 5f. And for nobelium, it is the second to the last one. And since F has 14, it is F13. And that's it. 7s2, 5f13. Let's look for yttrium. Yttrium is Y. My eyes. Okay. Yttrium is element number 39. So we go up 1 and all the way over. The last noble gas for yttrium is krypton. Why am I not doing bismuth? I don't have enough space. Okay. So with that, to do the configuration for the row that yttrium is on row 5. So we go with 5s2. After 5s2, yttrium is in the D section. So we drop down 1 number lower to 4d. And since it's the very first one, 4d1. Okay, drop it orbital diagram for neon. Neon is element number 10. So we will have 1s, 2s, 2p, 3s just in case. So 1s, 2s, 2p, 3s. Let's see. 1, 2, 3, 4. And if they're equal in energy, in the p, because all equal, remember single first. 5, 6. That's what 6 would look like. 7, 8, that's 9, 10. So for neon, we only need 10. We don't need to get to 3s. So just did that just to note to you that on the test, if you have more than enough space, you don't have to fill them all in. You just fill them enough to get to your number. Potassium is K is number 19. So we go same thing again. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and therefore we need one more, which is now 4s, 19. Okay, so you ask for how many valence electron potassium have. You look for the highest principal quantum number, and you add it up. So in this case, potassium has 1. How many does neon has? The highest principal quantum number is not 3 because it's blank, it is 2. And since there's 2s and 2p, you add both of them together, it would have 8. So that's why neon is in family number 8. The Lewis dot diagram for neon would look like this. I'm reviewing that might as well. And then for potassium, it'll be just K with 1 dot. So with that, which element ends in 4d6? So you go down to 4d and you count the cross. So it's in that row that has deuterium we just did. So 1, 2, 3, 4, 5, 6 is all U. 6s1, we go to row 6 and we go very first one. It is cesium. Which one is 5d2? So we go 3d, 4d, 5d, and it looks like it's HF. 5p2, we go 2p, 3p, 4p, 5p, and the second one looks like it's 10. Which element ends with 2p5? So we go to row number 2 and find the 2p, and the fifth one is fluorine. Draw the dot diagram. Sodium is in family number 1, 1 dot. Carbon is in family number 4, 1, 2, 3, 4. Oxygen is in family number 6, 1, 2, 3, 4, 5, and 6. Krypton is in family number 8, so 1, 2, 3, 4, 5, 6, 7, and 8. That's why krypton is a noble gas. It has 2 electrons on each side. Hopefully that helps. If you need anything else, welcome to come in early. Sorry for this being a little late, but I have other things going on for a little bit. My fault. Apologize.